Hi, in this video we discuss decay and integrability of Fourier transform. We will mostly need it in the context of C2 test functions. We know those are compactly supported, so they themselves are certainly integrable, but their Fourier transform will no longer be compactly supported. There is no reason why it should be. Therefore, we need a proof that the Fourier transform of a C2 test function is integrable. And we will state and prove a more general theorem to see where integrability comes from in general. And then the last part of this theorem will give us the results which we are mostly interested in. So the general theorem, so the first part, which will be the general part, says that if we have a function for which we will be doing the Fourier transform, so let h be a function from R to R, be such that the following three conditions are satisfied. Condition 1, or let me say A, is that h is m times differentiable and its mth derivative is continuous. Continuous. People often use notation Cm for this, similarly how we use C2 for functions which were twice differentiable with a continuous second derivative. So M stands for how many times you can differentiate, C stands for the continuity of the last derivative. Okay, so the second assumption is that h and all its derivatives up to the last one, the mth one, are Lebesgue integrable. So hi is Lebesgue integrable for all I between 0, so 0 corresponds to the original function, until m. And last assumption is I want all the derivatives, including my original function, so again I'm writing hi, to have the property that it tends to 0 at the ends, so when t tends to plus and minus infinity. So as t tends to, maybe let me say it like this, t tends to infinity, and this is again, for all I starting from 0, but now I don't need this condition for the last derivative, just for the previous one. You will see why. So if those three conditions are satisfied, then we can say that at the ends h decays as so at most as t to the power minus m, or maybe faster. So then there exists a positive constant such that the Fourier transform of h, so if I said h in my previous sentence, I should correct myself, so I'm talking about the Fourier transform of h, and that one is bounded by c over t to the power m for every t. I should say different from 0, because for 0 this formula doesn't make sense, but it's not important because I'm only interested in this estimate when t is large in the absolute value, because when t is small, this is a very bad estimate. It tends to infinity when t is close to 0. So on the picture, it means something like this. So we have our bound, which looks like c over t to the power m. I don't even want to draw it properly for small values of t, because it's not really helpful there. And you see, I'm also drawing minus c to the power t, minus c divided by t to the power m, because my estimate is going to be for the absolute value of the Fourier transform. And then this estimate simply says that the Fourier transform should lie between these green curves. So it can oscillate like this. Then I don't know at all what it does in the middle, and I'm not interested. And maybe it doesn't oscillate on this side, but just remains positive, so no one knows. But what's important is that I know it is not bigger than t to the power minus m times some constant around plus and minus infinity. So this is the general statement, and you see the idea behind it is that the smoothness of your original function h translates into the decay of the Fourier transform at the ends. So the more smooth your function h is, the faster your Fourier transform will decay. Okay. Now, second part is devoted to C2 test functions. So let h be a C2 test function. Then there exists C such that, in fact, the proof of this second part will be trivial once we have proved the first part. So look, if we have a C2 test function, then clearly condition A is satisfied with m equals 2, right? Simply because it means exactly the same. Secondly, since our function h is now compactly supported, so will be all its derivatives. I mean, all meaning the first derivative and the second derivative. We don't know if any further derivatives exist, but h first derivative, h second derivative will all be compactly supported, and therefore they will be integrable, and therefore they will tend to 0 as t goes to plus and minus infinity. So we can already apply the first part of the theorem and say that there is a constant such that the absolute value of the Fourier transform of h is bounded by c over t squared, because the level of smoothness is 2 now, for every t different from 0. And in particular, I'm going to say that the Fourier transform is integrable. Why? Because so the Fourier transform is continuous, so it's definitely integrable on any finite interval. And then at the ends, we have this bound by a constant divided by t squared, and this bound is integrable, and therefore our function will be integrable too. So in particular, so you see here it is very important that our function is twice differentiable. If it was differentiable only once, in our bound we would have t to the power 1, so just t, and 1 over t is not integrable. So we wouldn't be able to prove integrability of the Fourier transform of a function h, which is just differentiable once. Okay, let's agree we don't need to prove second part, but we do need to prove the first part. So proof part 1. all what we will need to do here is integration by parts. So let me write down the definition of the Fourier transform. It's the integral from minus infinity to plus infinity e I t x h of x dx. And I want to integrate by parts, so I will move the exponential function under the differential, which will give me h of x d e I t x. And to make this formula correct, I have to divide by it. And now the integration by parts formula tells me that so it tells me, don't forget the factor 1 over it, and then I need to take the product of h and e to the power itx and substitute minus infinity and plus infinity here. Maybe let me emphasize that this is for the variable x, because all integration happens with respect to x, minus the integral from minus infinity to plus infinity e I t x h prime x dx. Now, what happens if I substitute plus infinity and minus infinity for x? This term is bounded by 1, and this term tends to 0 by one of our conditions, and this is why we needed it. So this term equals 0. Maybe let me just cancel it. And we are left with this factor, and otherwise very similarly looking terms to our original one. The only difference being that now we have this extra factor, the minus sign, and the derivative of h instead of h. By the way, we used the integrability of h to be able to say that the Fourier transform makes sense, and to be able to write this formula also, because for this integral to make sense, we need that h prime is integrable. And we also use that h is differentiable explicitly here, because we write the derivative of h, but also that the first derivative is continuous, because this is one of the requirements of the integration by parts procedure. So this we needed to do one step, but we will now do m steps like this. You can say by induction, or you can just say by repeating this procedure. So I'm doing this m times, and this gives me minus 1 to the power m, it to the power m, integral from minus infinity to plus infinity, e I t x h m x dx. So you see, to be able to repeat it m times, I need integrability up to level m. I need continuous differentiability up to level m, but I only need these terms to go to 0 until level m minus 1, because to reach level m, I will be using this for h m minus 1. So this is why we need these conditions, and this is how we use them. So now if I want to finish my proof, I will look at the absolute value of h, which will allow me to get rid of this term, also of I, because the modulus of I is 1 anyway. So from all this ratio, I will have t to the power minus m. So 1 over t to the power minus m. Now the integral, I have the absolute value outside of the integral at this stage, but we know that we can bring it inside if we want an upper bound. So it will be the integral. So I could write an upper bound with the absolute value inside. So maybe let's do this one extra step. And also I will write it separately for both terms because it is, so it doesn't make any difference. Then, of course, this absolute value is just equal to 1. And since the nth derivative of h is Lebesgue integrable, this integral is finite. This is the definition of being Lebesgue integrable. And I can take the value of this very integral as my constant c. So this with or without this symbol here, because it's just 1 anyway. So this is how I get c over t to the power m. And maybe let's add that the second part we agreed is quite obvious. One small example to illustrate this theorem. So I suggest we look at the normal distribution. And we know its density is 1 over square root of 2 pi e to the power minus x squared half, right? So I want to look at the Fourier transform of f, which is the same, of course, as the characteristic function of the normal distribution. And I want to know how fast it decays at the end. So look at this function here. Clearly, it's smooth. We can differentiate it any number of times. Also, all the derivatives will look like this exponential term here times some polynomial, which means that this term will always win when x is large and will make everything very small. So all the derivatives of f will be Lebesgue integrable, and they will tend to 0 at plus and minus infinity. What does this theorem tell us then? It tells us that the Fourier transform will decay at the ends faster than any power of t. And we just know explicitly what the Fourier transform is. We know it's e to the power minus t squared half. And we see that it is indeed true that it decays faster than any power of m. So decays, so let's say indeed decays faster than any 1 over t to the power m. I don't need a constant here because I'm saying that's true for any power m anyway.